Okay. Now, following this example, I will continue with a few properties, a few further properties of the discrete time Fourier transform. The second property that I'm going to indicate is differentiation. But it does not exist in discrete time. We do not really take the derivative of differentiate, but we take the difference, so we can say differencing, which automatically makes this property not really a proper property, but it's an easy one, which can be easily achieved. The difference is this, xn minus 1. And the corresponding discrete time Fourier transform from here is x of e to the j omega, which is from x of n, minus e to the minus j omega x of e to the j omega, which is the shifting property that I didn't list out, but it's easy. We know it from continuous time already. If you shift in time, you multiply in frequency domain with e to the minus j omega times the amount of shift, where the shift is 1 here. So the right-hand side of the Fourier transform pair becomes 1 minus e to the minus j omega in parentheses of x of e to the j omega. Okay? And that is the property. As you see, it's not even a property, it's too easy. Notice that in continuous time, this was j omega in continuous time. We were multiplying x of j omega, capital X of j omega, with a j omega. But now we are multiplying it with something more than that. It's not more, but it's different. It's a little bit different, and it has a similarity, an interesting similarity. For those of you who are curious, just try to plot this using MATLAB or any other tool you may have. Please try to plot this 1 minus e to the minus j omega. Of course, it's complex, so don't plot itself, but plot the magnitude of it, okay? The magnitude of this complex entity. Between pi is, let's say, minus pi over, omega is between minus pi over 4 to plus pi over 4. Within that range, plot this. Plot the magnitude of this. And also plot the magnitude of j omega. The magnitude is the absolute value of omega, of course. It's easier than this one. Between omega between minus pi over 4 and pi over 4, you will see that the shapes somehow resemble each other. They both have this V type of shape. But the one that we have for the discrete time case, 1 minus e to the minus j omega, is there because j omega is not 2 pi periodic. So if you multiply a 2 pi periodic signal with j omega, it becomes aperiodic. It spoils the 2 pi periodicity. But if you multiply a 2 pi periodic x of e to the j omega with 1 minus e to the minus j omega, which is also 2 pi periodic, then it will remain 2 pi periodic. So this thing is the discrete time version, and it has to have a 2 pi periodicity intrinsically. So this is the differencing that we have, and it helps us to obtain the integration, which in discrete time may be considered as accumulation, because it is telling me that let's say for m from minus infinity up to n, up to the index of the signal, x of m. So I'm accumulating all the way from minus infinity up to the time instant of n. This accumulation will have the discrete time Fourier transform, which is equal to 1 over 1 minus e to the minus j omega, the inverse operation of the Fourier transform, times x of e to the j omega. Unfortunately, that's not all, but it's there. It's like putting 1 over j omega in integration. if you may remember. But you may also remember from the continuous time Fourier transform, the integral has something else. It has here a plus pi times capital X of 0 or capital X of omega at omega is equal to 0 times delta of omega. You may remember that, okay? You may check your notes. Here, something similar is happening. This is also capital X of 0, but it is capital X of e to the j0. I'm writing it like that to indicate that omega is equal to 0. In fact, e to the j0 is e to the 0, which is 1. So this is capital X of 1. Capital X of 1 corresponds to the discrete time Fourier transform at omega is equal to 0. It's a little bit confusing. So I don't want to confuse you, and I'm leaving it like this. It's the 0 frequency and an impulse. But this impulse at omega is equal to 0, the DC, I have to make it 2 pi periodic with the other impulses as well. So I don't only have delta of omega, but I have an infinite summation of impulses like this, delta omega minus 2 pi k. So it's not delta omega only, it is summation for all k, delta omega minus 2 pi k. Because if I have only one impulse in the center of the frequency axis, and it is added to a 2 pi periodic signal, a 2 pi periodic Fourier transform, this impulse, when I add, makes everything spoiled. It won't be 2 pi periodic anymore. I have to have an impulse at 0, and I have to repeat them. By the way, there is an open microphone which is making some background noise, so I may ask our friend to turn it off. Although I like it that way, you know, I can have some amount of feedback as I'm talking. It's very difficult to talk to a blank screen with absolutely no audio. It's like talking to the wall, and I cannot really get a feedback that you are there. So when I hear some kind of background noise, it helps me to think that you are there. Anyway, it's noise anyway. So integration and accumulation is therefore the reverse of the differencing operation. The third property that we can talk about is upsampling. Upsampling is like scaling in time. So what we really have to do is we have to remember maybe this. Scaling in time was like this, right? X of a times t will have a continuous time Fourier transform, which is equal to 1 over absolute value of a, capital X of j omega over a. So if you are multiplying in time, if you are multiplying t, then you have to divide omega. You divide in the frequency domain. This was the time scaling. Upsampling is somehow like this. I will indicate the upsampling with a subscript of k. X subscript k of n is x of n upsampled by k, and it is actually analytically notating would look like this: capital X of n over k, when n is an integer multiple of k, and it's equal to 0 else. This analytical formulation may look awkward to you, but it actually looks like this. It starts from a signal, let's say this, 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 and this. Suppose this is x of n, then x sub 2 of n, which is an upsampling by a factor of 2, is essentially like stretching the signal, a discrete time signal. You're pulling from both sides of the signal. But since it's discrete, when you stretch, you have to stretch by integer amounts only. And you have to insert zeros in between because there will be gaps. This is at 0, this is 1, this is 2, 3, 4. If you stretch it twice, there will be empty gaps in between. And instead of those empty gaps, you put zeros. So the signal becomes like this 0, and then this 0, and then this 0, and then this 0, and this, etc. It becomes like this. The upsampling makes stretching in time and insert zeros in between, okay, for all the gaps that occur. That is called upsampling. But it is like scaling in time. It's like x of n over k. What is the corresponding Fourier transform then? When you do this, you divide the time by k, it means you are in the frequency domain, you are multiplying omega by k. So the Fourier transform, discrete time Fourier transform of this one will become, you can put it inside the formula and see the same thing. It's easy to obtain this. Capital X of e to the j times k times omega. Because you are dividing n by k, you have to multiply omega by k. And by the way, you don't have anything like this. You don't multiply this by the absolute value of k, which should be the case if you're having continuous time. But here, this time, we don't have it. The reason that we don't have it is because the total energy of the signal does not change in our case. In continuous time, if you stretch a signal, there will be no gaps. It's continuously stretched, so it's like interpolating and inserting some new values at these points where now they are zeros. So you are interpolating the signal in continuous time. It's getting larger, and larger signals will have more energy. And because of that, we would have magnitude of k times or magnitude of a if you have a continuous scaling of a. But now we don't have it because the energy does not change. We are inserting zeros and we are keeping the energy of the two signals, x of k and x of n. They have the same energy. Therefore, we don't have this absolute value of k, but we only have this. But this is the easy part, the upscaling, or upsampling. X of n over k will correspond to a Fourier transform of capital X of e to the j omega times k, or k omega. Downsampling, on the other hand, is difficult because its discrete time Fourier transform is not simply like e to the j k omega over 2. Okay, because if e to the j omega, if capital X of e to the j omega is 2 pi periodic, unfortunately, capital X of e to the j omega over 2 is not 2 pi periodic. It will be 4 pi periodic. So it's not going to be 2 pi periodic. Therefore, the downsampling Fourier transform is not simply this one. Fourier transform is not this, because it's not 2 pi periodic. It is something else. We must make it 2 pi periodic. If you go into the details of digital signal processing, which is starting from discrete time signal processing, this one is discrete time Fourier transform. It's a part of digital signal processing. If you take the courses of digital signal processing in the last year electives, you will see that this is one is x of e to the j omega over 2 part is 4 pi periodic, So let's make an extra shift of that by 2 pi, another extra component, and then add it to this one, and it will become 2 pi periodic. Yes, that would correspond to the discrete time Fourier transform of the downsampled signal. If the downsampling factor is 2, if the downsampling factor is 3, then you have to add extra 2 components because it will be periodic with 6 pi. So you need a 2 pi shifted version to be added and a 4 pi shifted version to be added to make everything 2 pi periodic. But this is a concept which is very much focused in digital signal processing. So I'm not going into the details of this, and I'm not going to show it to you. You can check out those things. And it's important in digital signal processing, by the way. But for the time being, you will be responsible only for upsampling, whose Fourier transform is easy. It's there. And it is logical, easy to understand. The other one, the downsampling's Fourier transform, I can write down the formulas if you wish, but you won't be responsible for those things. So I'm just totally omitting this one, and I'm forwarding you to the digital signal processing courses. All right, this was upsampling and downsampling. Do we have anything else? Yeah, we may think of convolution and multiplication. Which is that? The fourth property, convolution and multiplication. The convolution is simple. We know it, right? X of n convolution with h of n will have a discrete time Fourier transform corresponding to x of e to the j omega times h of e to the j omega. That is the simple convolution. And from something like duality, okay, there is a duality, by the way. Am I going to talk about duality? Yes, but the duality, unfortunately, is only appearing in the discrete time Fourier series because of this. If you have x of n, its Fourier transform is capital X of e to the j omega. And here at the right-hand side, it is continuous time and it is periodic. So we don't really have anything that relates that continuous time and periodic signal with this discrete time normal signal, not necessarily periodic. So the duality does not work that way, but it works as the discrete time Fourier series coefficients of this continuous time Fourier transform shape. It's a shape, it is periodic, so it's a continuous time periodic signal. And we know that they have the Fourier series coefficients. The Fourier series coefficients of those are related with these discrete time signals. I will show that. But before that, I will use it a little bit to give you this multiplication in time domain property. If you have, for instance, y of n, so this is an example, but it's a counterexample to the convolution property. Y of n is equal to x1 of n times x2 of n, okay? Then the Fourier transform of y of n, which is y of e to the j omega, will be equal to the convolution of x of e to the j omega, x1 of e to the j omega, and x2 of e to the j omega. I have to convolve them. But remember that x1 of e to the j omega and x2 of e to the j omega are periodic. So I have to apply a periodic convolution, which is a little bit different. First of all, the periodic convolution integral, the amount of shift is not from minus infinity to infinity after folding back and sliding. You remember convolution. We are folding one of the Fourier transforms. It could be the Fourier transform of x1 or x2, but the amount of shift that I apply is only within a range of 2 pi. I may shift from 0 to 2 pi, or I may shift from minus pi to pi, make that kind of a 2 pi limited amount of shift. And I put, for example, the Fourier transform of x1 as x1 of capital X1 of e to the j omega, and I fold the other one, x2 e to the j. So how do I fold it? But of course, I'm sorry, this is not omega, it is the tau, okay? So x1 of tau, x2 of t minus tau. x1 of tau, instead of tau, I have to use something else because tau is related with t. So for omega, I use, let's say, theta. This is like tau, okay? And t minus tau in the second one is omega minus theta, okay? D tau is d theta. So this is an interesting overall convolution expression. It's interesting because the parameters are in the exponents, which makes the notation a little bit awkward and difficult. Like omega tau, instead of omega, instead of t, I use omega. Instead of tau, I use theta, and they are in the exponents. And of course, it is only with an amount, shifting amount of 2 pi because this is a periodic convolution. All right. Do we need examples of these? We can give examples, but even this slightest example will take a lot of time. For instance, think of x1 of n to be a low pass signal whose Fourier transform is like this. Okay, this is x1 of e to the j omega. x2 of e to the j omega is, let's say, also another low pass, maybe a little bit wider like this. Like this. This is x2 of e to the j omega. Now, periodic convolution is a difficult thing. You have to flip around maybe x2 of e to the j omega and start shifting to the left and sliding to the right. But shifting to the left is not indefinitely. It's not from minus infinity. You shift to the left by an amount of, let's say, pi. So the shift is minus pi. And from there, you start shifting to the right up until pi. From minus pi to pi is the amount of shift after flipping around. By the way, when you flip around x2 of e to the j omega, it gives you the same shape because it is symmetric. And then some portions of x1 and x2 will overlap, and those portions will maybe, I'm not sure, I haven't drawn the widths accordingly, but it will be overlapping all the way and then increased in overlap and then decrease in overlap and something like this. So the periodic convolution of these two will probably give you some shape like this. If you don't understand why it is this way, so this is x1 periodic convolution with x2 on the frequency axis, I can intuitively see that the answer will look like this. I think there will be a similar example in the book. I urge you to consult that example to understand why this is like that. Because as you see, when you shift x2 by some amount, one component from the left-hand side and the other component from the right-hand side will all contribute to the multiplication. They may have overlaps with x1. So after some time, it starts increasing back, decreasing and stay constant and then increase again. This is an interesting situation. And it's not very easy, unfortunately. I don't think I intend to ask a question about that, but it's good to know it. Okay. Okay, now the last thing about the properties of the discrete time Fourier transform, and that will be the last discussion regarding today. is the duality property. Sorry. The duality is the fifth property that I want to mention. Of course, there are many more properties. They are all listed in the book. These are the ones that I find worthy of giving examples. The duality, as I say, will not be in the form of the signal and its discrete time Fourier transform itself, but the signal itself must be a periodic signal, which makes its discrete time Fourier transform to be sampled and periodic as well. So it's more like a duality in the discrete time Fourier series. Duality in the discrete time Fourier series. I have to say it like this. And the duality property is like this. If you have a periodic signal, f of n, then you will have its discrete time Fourier series as a case, right? Like this. And I'm going to denote these a case as, I don't know, g of k's, because it is a discrete function of k. And this is periodic with n, with, let's say, capital N. Then gk is also periodic with capital N, you know. We have capital N distinct Fourier series coefficients, and then they repeat themselves. So gk is also, therefore, a periodic signal. Now I take this gk and make it my new discrete time signal. It was previously the Fourier series coefficient. It was a signal in the frequency domain corresponding to the harmonics, but now I say it's the signal itself, the discrete time signal, which will have, since it is 2 pi periodic, it will also have Fourier series coefficients that we call bk's, which are also periodic by capital N, and these bk's are related to 1 over capital N times f of minus k. You see, f of n was our original signal. Now I have f of minus k. It's the flipped around version of f of n, in other words. So we can relate this and this, f of n and f of minus k, it's there, which is telling me something that may be useful in solving some of the questions. Like if a signal is given to you, but you remember that signal from the table that you have, which appears as the discrete time Fourier series coefficient formula of something. So it doesn't look like a signal that you have seen before, a discrete time signal, but it actually looks like something. So this signal g of n looks like something of the discrete time Fourier series coefficient formula of another signal. So what is that other signal will therefore be the Fourier series coefficients of your new signal. For instance, if you have a rectangular box train, periodic, so a rectangular box train is there, and we know that its Fourier series coefficients are like sinc. Now I give you a sinc signal in discrete time. What are the Fourier series coefficients corresponding to that? They will be rectangular box trains. Okay. The time signal versus the frequency signals can be used in some ways interchangeably within some scales of 1 over n, and they must be folded, of course, as f of minus k. This is very much similar to the formula that we use for continuous time Fourier transform. But in continuous time Fourier transform, it was easy. and it doesn't really require anything like a periodicity of these Fourier series coefficients, but in discrete time, we don't have it for the discrete time Fourier transform. We have it for the discrete time Fourier series, unfortunately. So these are the, this was the last property that I want to indicate. Now, apart from these, as we did in the last, as a last issue of the continuous time Fourier transform, what was the last issue that we covered from continuous time Fourier transform? The differential equations. How do we convert differential equations in time to expressions or equations in the frequency domain by taking their Fourier transforms? And it was in the form of j omega. For every derivative, we put a j omega in the Fourier transform. If it's a second derivative, it's j omega in parentheses squared. If it is the third derivative, it's the cube of j omega, etc. That's how we found the frequency response and the system transfer functions. In discrete time, something similar happens. And it happens like this. So this is the difference equations. These are the difference equations that I want to talk about. And I want to give this lecture of difference equations only through one example, because then you will understand. And the other difference equations will be just extensions of this one. And the difference equations are interestingly both for the input x and the output y, like the differential equations that we covered. For instance, a first order difference equation is the following. This is the difference equation. yn minus a yn minus 1 is equal to x of n. It could be longer on the y part, and it could be longer on the x part. And we know, for example, how to draw the block diagrams, the simplified or the reduced form of the block diagrams using delay operators, etc. It was an issue of the first midterm, if you may remember. But now I ask you one simple question, which could be obtained without the analysis that we will do now, but you can do it in an easier way. We will see that. Can you give me the impulse response of this input-output relation, the difference equation? How can you find the impulse response? You can find the impulse response with an assumption that it was initially the output initially was 0. You put, instead of x of n, you put delta of n, apply it, and solve for y of n. You see that y of 0 is minus 0, y of 0 minus 0 is equal to delta n at n is equal to 0 is 1. So y of 0 is 1. Then y1 minus a times y0, which was 1. So y1 minus a is equal to 0, which means y1 is a. And then you will find y2 is equal to a squared. y3 is equal to a cubed. You can iteratively solve this to give me the impulse response, okay? And I can see that h of n is equal to something like this. 1 when n is equal to 0. It is a when n is equal to 1. It's a squared when n is equal to 2. It's a cubed when n is equal to 3. And it goes on like that. And it is 0 when n is less than 0. Which can be written in a compact way as a to the n times u of n. So h of n is a times a to the n u of n. I can solve it just intuitively by iteratively decoding this expression. But now I'm going to show you the proper way of solving this. I will take the discrete time Fourier transform of both sides of the equation, and it's going to give me y of e to the j omega minus a times e to the minus j omega times y of e to the j omega is equal to x of e to the j omega. So let's put the left-hand side into a parentheses of y of e to the j omega, which is 1 minus a e to the minus j omega, y of e to the j omega is equal to x of e to the j omega. And from convolution versus multiplication, y of e to the j omega over x of e to the j omega will be equal to h of e to the j omega, right? And that is equal to 1 over 1 minus a e to the minus j omega. So I found the frequency response of the system, which is this. Can you find the inverse discrete time Fourier transform of this? Yes, by looking at the tables, and you will immediately notice that will give you h of n is equal to a to the n u of n, because 1 over 1 minus a e to the minus j omega is the Fourier transform of a to the n u of n. It was our example number 1. You see, I found it in a proper way by writing the difference equation and taking the Fourier transform of it. And fortunately, or luckily, I could obtain y of e to the j omega over x of e to the j omega expression in a parentheses form, and I call it h of e to the j omega, and I obtain it like this, and its inverse discrete time Fourier transform is a to the n u of n. Okay. So the difference equations are convertible to frequency responses. Let me write them in a different color. This is the frequency response. Which can be inverted in Fourier transform by taking the inverse Fourier transform to give you the impulse response. Okay. So difference equation, frequency response, and impulse response are there. It's like differential equations versus frequency response versus impulse response. These things are critical, and I usually ask questions about these. I give you, but the question may be in a reverse manner. I can give you the impulse response, like h of n is equal to a to the n u of n, and I may ask you the difference equation, which gives or describes the input-output relation. How do you find it? You take the Fourier transform of h of n and obtain h of e to the j omega. Okay, the frequency response you get. Write it or put it in the form of y of e to the j omega over x of e to the j omega. Make cross multiplications, write them as this line, and then take the inverse Fourier transform of both sides of the equation to come up with a difference equation. That's how we do it. Can you do that in an examination? Hopefully you can. It will be, what kind of a question can you obtain? Of course, a second order question may arise. And let's see if you can find the difference equation related to a second order H. Okay, I will generate or exemplify a second order H. How am I going to construct the question? Can you imagine? I will take the, or I will find the impulse response of this y of n. Let me write it like here. I will think of it, constructing a question like this. I will say y of n minus a y of n minus 1 minus b y of n minus 2 is equal to x of n minus c times x of n minus 1. I will start from here, and I will find h of n for, of course, some certain values of a, b, and c. I will give numerical values to that, and I will find h of n, something. And in the examination, I will give you this h, and ask you what is the difference equation. Is that clear? Do you understand how I'm going to ask the question in the final? And as you see, when I promise to ask some questions, in a sense, I do. So please study this one. This is something that you will encounter. And when you study, of course, professors or teachers are, bad people. You work for it, and I make a very small alteration to the question. I put a 2 times y of n here. And suddenly things change, and you come up with some awkward situation when you're solving, because if there is a 2 times y of n, you can easily divide all the equation by 1/2 and still obtain a similar expression like this. Okay. So questions are many. I will just generate and ask you in an examination, and I hope it's all clear now. All right, that concludes the discrete time Fourier transform. Sort of. Of course, the continuous and the discrete time Fourier transform and the Fourier analysis from now on will also be valid for all the other topics that we will see. We will very briefly see sampling in the next hours. We will start to talk about sampling. Over there, of course, Fourier analysis, continuous time and discrete time Fourier transforms will be important. But anyway, and afterwards we will see the Laplace transform, which is an extension of the continuous time Fourier transform, and the Z transform, which is the extension of discrete time Fourier transform. So these Fourier analysis is something that you have to always keep in your minds, and you have to always keep in your minds the concepts of convolution too. Okay, never forget those things. So some students ask from which parts are we responsible in an examination, and that's an invalid question, because in order to solve a question which is related to the last topics, you have to know everything until there. You have to know convolution, you have to know the Fourier transform, you have to know the Fourier series. Everything is connected to one another. Okay, that's the answer to a question that you may think of. Already I'm giving you the answer to that. Okay. Any questions? Are there any questions that you may have? Okay, as I see no questions, I'm stopping the recording, and on Wednesday we will meet at the same place. Okay, until then, take care. See you.